Swayam Prabha. Digital India. Educated India.
Hello student, welcome to the course on optimization methods for civil engineering. So, today we will continue our discussion from the part we have discussed in the last class. So, in the last class I introduced you what is optimization, then also we discussed few example problems. Basically we discussed how we can formulate an optimization model, and also we have discussed what is optimization. Let us consider a single variable optimization function. So, we are not considering any constraint here, or in that case we are calling it unconstrained optimization problem. Now, so we have only the objective function. So, we have the objective function f x. Now, this objective function can be a minimization function or a maximization function. So, here we do not have any constraint. So, therefore, this is an unconstrained optimization problem, and we are only considering one variable, that is single variable, and therefore, this is single variable optimization problem. Let us discuss what is stationary points. For a continuous and differentiable function f x. So, here f x is a continuous and differentiable function. A stationary point x star. So, x star. So, when the point is stationary, then we will denote it by x star. So, that means x star means it is a stationary point. A stationary point x star is a point at which the slope of the function is 0. Okay. That means the first derivative is 0 at x equal to x star. So, otherwise what I can say, that if first derivative is 0, that means slope of the function is 0 at x star. So, in that case x star is a stationary point. I hope this is clear. So, what is stationary point? The first derivative should be 0. That means slope of the function at that particular point is 0. So, in that case x star is a stationary point. Now, let us consider this particular function. So, here we have one point. So, this is a stationary point, that means the first derivative is 0 here. So, at this particular point the first derivative. So, this is a stationary point. So, I will write x star, and this is equal to 0, but this is also a minimum point. Why minimum? That if I go, so I am at x star right now. So, this is the point x star, this is the point x star. So, I am at x star. So, if I go slightly right hand side or left hand side, my function value will increase. That means, this is the minimum point of this particular function, and if you go slightly on the right hand side or left hand side. So, if you go on this direction or in this direction, the function value will increase. So, therefore, this particular point is a minimum point. Now, let us consider this particular function. So, here we have a stationary point. So, why it is a stationary point? Because the first derivative at this particular point is also 0, but this is a maximum point. Why maximum? Because if you go slightly right hand side or left hand side, in this case the function value will decrease. So, therefore, that is the maximum of this particular function, and if you go slightly on the right hand side or left hand side, the function value will decrease. So, therefore, that is a maximum point, but this is a stationary point. Why stationary? Because the first derivative is 0, or you can say the slope of the function is 0 at that particular point. Now, let us consider this particular function here. Now, this is a point here. So, again this is your x star, and at this point the first derivative is 0, first derivative is 0. Therefore, this particular point is also a stationary point, slope of the function is 0 at this particular point. So, therefore, this is also a stationary point, but this is neither maximum point nor minimum point, because if you go in this case, if you go right hand side, the function value will decrease, and if you go left hand side, the function value will increase. So, therefore, this particular point is neither a minimum point nor a maximum point, but this is an inflection point, and we call it inflection, but this is also a stationary point. Now, from these example problems, so we can conclude that a stationary point may be a maximum point, may be a minimum point, or may be an inflection point. So, your function may be like this also. So, in that case also this particular point may be an inflection point where derivative is 0. So, therefore, the stationary point does not mean that that particular point will be a maximum point or the particular point will be a minimum point, but it will say that this particular point is a candidate for either minimum point or maximum point or an inflection point. I hope this is clear to you. So, what is stationary points? Now, in this particular curve, so I have shown you a function. So, if you look at this particular function, a1 is a point and this is a maximum point, then a2 is also a point, this is also a maximum point, and a3 is also a maximum point. Okay. Or you can say these are all stationary points. Why stationary? Because the first derivative is 0 at a1, a2 and a3. So, first derivative is 0. The slope of the function at this point is 0. Similarly, if you look at the first derivative is also 0 at b1 and b2. So, therefore, a1, a2, a3, then b1, b2, all these points are stationary points because the first derivative is 0. Now, if you look at the point a1, a2 and a3, so here what is happening, if in case of a1, if you go slightly right hand side or left hand side, the function value will decrease. So, therefore, this is a maximum point. Similarly, a2 also, if you look at, if you go on the right hand side or if you go on the left hand side, the function value will decrease. So, therefore, this is also a maximum point. Now, if you go to a3, here also if you go on the right hand side or left hand side, the function value will decrease. So, therefore, a1, a2, a3, these 3 points are maximum point. Now, one of them that means either a1, a2 and a3. So, one of them is basically the best solution within the search space. So, in that case what I will say, the best solution will be the global maximum solution. So, in this case a2 is the best solution out of a1, a2 and a3. So, therefore, a2 is your global maximum. I hope this is clear. So, let us see the definition of what is global minimum or what is global maximum. So, a function is said to have a global or absolute minimum at x equal to x star. So, x star is a stationary point if the function value at x star is less than f of x for all x in the domain over which f of x is defined. So, here the f of x is defined between a and b, and within that domain that a2 is the best solution, and you can say that is the global maximum solution, or if I say in case of minimum. So, b1 and b2 are minimum point here, and b1 is the best solution, and therefore, you can say that b1 is the global minimum. So, similarly, I can define global maximum point and global minimum. So, global maximum is a function is said to have global or absolute maximum at x equal to x star if the function value at x star is greater than f of x for all x in the domain over which the fx is defined. So, if I look at this definition, what is global minimum and global maximum, global minimum and global maximum. So, if I look at this definition and this particular function, so A2 is the base solution, that means the base maximum solution. So, I can say that A2 is global maximum. Similarly, B1 is the base solution in terms of minimum point. So, therefore, I can say B1 is your global minimum. Now, A1, A2, A3 all are relative maxima, or you can say these are local optimal solutions. So, A1, A2, A3 are relative or local maxima, and similarly B1, B2 are also relative or local minima, but A2 is the global maximum solution and B1 is the global minimum solution. I hope the difference between local solution and global solution is clear to you. So, what we call it global solution, that is the base solution over which the function is defined in terms of either minimization problem or maximization problem. So, in this particular function B1 and A2 are the base solutions. So, B1 is the global minima and A2 is the global maxima, and all other solutions are either local maximum solution or local minimum solutions. Now, I have shown here two different functions. The first function is f equal to twice x to the power 4 minus 7 x square minus half x plus 6, and if I plot this particular function between minus 1.5 and 1.5. Okay. So, within minus 1.5 and 1.5. So, you can see that this particular function has one stationary point somewhere here, another stationary point somewhere here, and another stationary point somewhere here. So, this particular function has two minimum points. So, two minimum. So, this is one minima, this is another minima, and it has one maximum point. So, if I say that if I compare these two minimum solutions, then one is the base solution. So, this is the base solution of this particular function. So, therefore, this is global minimum and other one is local minimum. Similarly, we have only one maximum solution, and therefore, you can say this is the local maximum point, or you can say because we have only one maximum. So, therefore, that is the global maximum point of this particular function. Or so, now if I look at this particular function, the second function, the function is f equal to sin x exp within bracket minus absolute value of x by 5, and we are defining this particular function between minus 3.2 pi and plus 3.2 pi. So, between minus 3.2 pi and plus 3.2 pi. So, you can see there are several stationary points. What is stationary point? The first derivative is 0. So, this is one stationary point, this is another 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 stationary point, and this is also a stationary point. Why stationary? Because the first derivative is 0, the slope of the function at these points will be 0. So, therefore, they are stationary point. Let us see whether there are minimum point or maximum point. You can see this particular function within this range, that is range is minus 3.2 pi and plus 3.2 pi. So, we have two minimum solutions. So, one is here. So, this is the first minimum solution and this is second minimum solution, and one of them is the base solution. So, I can say that this is your global minimum and other one is local minimum solution. So, we have another one. So, another minimum. So, somewhere here. So, we have total 3 minimum solutions in this particular function, and out of these 3, one is the base solution and that is the global minimum solution of this particular function. And if I look at the maximum point, so we have 3 maximum points. So, this is number 1, this is number 2 and this is number 3. So, you can say all of them are relative maximum, and one of them is the base solution, and the base solution here is this one, and you can say that that is the global maximum solution of this particular function. So, we have 2 local maximum points and 1 global maximum. So, therefore, this is your global maximum point of this function and other 2 are local maximum point. Now, let us see this particular function. So, you can see that this particular function has 1, 2, 3, 4, 5 stationary points. So, why stationary points? Because the first derivative at this point is 0. So, first derivative is 0. So, therefore, these points are stationary point, and these points are maximum point, because if you go slightly right hand side or left hand side, the function value will decrease. So, therefore, this is a maximum point. Similarly, here also the function value will decrease if you go on the right hand side or left hand side, similarly here also, similarly here also and similarly here also. So, therefore, all these 5 points are stationary point and they are also maximum point. So, you can say these are the maxima of this particular function. Now, if I compare these 5 solutions, so one of them is the base solution and you can say this is the global maximum point, and other solutions are local or relative maximum points. Okay. So, other solutions are local solution, or you can say local optimal solution, local maximum solution or local maximum point, and one of them is the base solution, and I can say that is the global maximum of this particular function. Now, let us discuss what is the necessary condition for optimality. Suppose a function is given to you, then how you can actually tell whether whatever solution you are getting or a particular point is a minima, maxima or an inflection point, or whether it is a stationary point. Okay. So, we call it necessary condition for optimality. So, we will discuss here what is necessary and sufficient conditions for optimality. So, in this case, so I will take a function like this. So, this is a convex function. I will also discuss what is convex later on, but right now, so in this particular function we have only one optimal solution, or you can say one stationary point. Okay. So, now what is necessary condition? A function f x is defined, if function f x is defined in the interval a b, that means between a and suppose this is b, within a b, and has a relative minima at x equal to x star. Okay. So, this point is your x star. Okay. So, x equal to x star, where that x star is between a and b, and if the first derivative exists as a finite number at x equal to x star, then the first derivative is equal to 0. Okay. So, if this condition is satisfied, so I will say that the x equal to x star is a relative minima. Okay. So, now what is the necessary condition? A function f x is defined in the interval a x b and has a relative minimum at x equal to x star, where x star is between a and b, and if first derivative exists as a finite number at x equal to x star, then the first derivative should be 0. Okay, if it is a relative minima. Now, let us prove it. So, how we can prove it? That I can write that derivative at x star which is equal to limit h tends to 0. So, f of x star plus h minus f of x star divided by h. Okay. So, I have taken this particular point which is x star, and you take another point at a distance of h. Suppose this distance is h, maybe I can also take another point which is at a distance h. Okay. So, this distance is also h. So, now I can write or I can take the derivative. So, derivative is equal to limit h tends to 0 f of x star plus h minus f of x star divided by h. Now, since x star is a relative minima. So, as already I said or already in the definition itself we said that x star is a relative minimum. So, this is the point x star and x star is a relative minima. If it is a relative minima, so therefore, f of x star should be less than f of x star plus h. So, what does it mean? That whatever function value here at f of x star plus h, that function value is more than f of x star if x star is a relative minimum. For all values of h sufficiently close to 0, okay, h tends to 0, then what will happen? Because this particular portion, okay, this particular portion is always positive, is not it? Because x star is a relative minimum. So, therefore, f of x star plus h minus f of x star is always positive. Okay. So, therefore, the sign of this one f of x star plus h minus f of x star divided by h will depend on whether h is positive or negative. Now, if h is positive, that means you are approaching x star from the right hand side. So, in that case this value will be greater than 0, and if h is negative, that means you are approaching from the left hand side. So, in that case this value will be less than 0. Okay. So, I hope this is clear, because f of x star plus h minus f of x star is always positive. So, the sign of this term will depend on whether h is positive or negative. H positive means you are approaching x star from the right hand side, and h will be negative if you are approaching x star from the left hand side. Okay. So, therefore, depending upon whether you are approaching x star from right hand side or left hand side, this value will be either positive or negative. Positive means greater than 0 or negative means less than 0. Okay. So, thus the derivative will be greater than 0 if h tends to 0 through positive value. That means, if you are approaching x star from right hand side, so in that case derivative will be positive, and if you are approaching from the left hand side, that means for h tends to 0 through negative value, so in that case derivative will be negative. Okay. So, I hope this is clear. So, what I am telling here, so if you are approaching from the right hand side, the derivative will be positive, and if you are approaching from the left hand side, the derivative will be negative. Okay. So, therefore, derivative will be positive based on how you are approaching to x star. Thus, only way to satisfy both the condition, that means at that particular x star these two conditions to be satisfied. So, therefore, the only way to satisfy these conditions is to have the derivative is equal to 0. Okay. So, therefore, this is the necessary condition for optimality, that means first derivative should be equal to 0. So, let us see the note here. So, this theorem can be proved for if x star is relative maxima. So, we have proved it for x star is relative minimum, but I can also prove it for x star equal to relative maximum. So, same way I can prove it. The derivative must exist at x star, that means the function must be differentiable at x star, otherwise you cannot apply this necessary condition. The theorem does not say what happens if a minimum or maximum occurs at the end point of the interval of the function. Okay. So, if the minima and maxima occurs at the end point, that means at a or b. So, this theorem we cannot actually, this theorem is not telling anything. And apart from that, so as I said that it can also be a inflection point. So, neither maxima nor minima. So, therefore, this is not the sufficient condition for optimality. So, it is a necessary condition that once the first derivative is 0, the particular point may be a maximum point, may be a minimum point, or it may be an inflection point also. So, but it is a necessary condition for optimality. Now, let us see what is the sufficient condition for optimality. So, if you apply the necessary condition, then the point, whatever point you are getting where derivative is 0, that means slope is 0. So, that point may be a maximum point, may be a minimum point, or it may be an inflection point also. So, therefore, I cannot tell whether that is a maximum or minimum or inflection point, but I know that this is either maximum or minimum or an inflection point. So, therefore, I need a sufficient condition for optimality. Now, let us see what is sufficient condition for optimality. Okay. So, sufficient condition, let us see the definition. Suppose at point x star, okay, this is an stationary point already, x star is a stationary point where first derivative is 0. Suppose at point x star the first derivative is 0, okay, because this is a stationary point, and first non-zero higher derivative is defined by n, and then if n is odd, x star is an inflection point. If n is even, x star is a local optimum, and then if the derivative is positive, then x star is a local minimum, and if the derivative is negative, then x star is a local maximum. So, here I am defining. So, it is a stationary point. So, x star is a stationary point. So, therefore, first derivative is 0. Suppose the second derivative is also 0, third derivative is also 0, fourth derivative is also 0, and n derivative is not 0. So, this is the n derivative of this particular function which is not 0. Now, what I will look? I will look at this value of n. So, now if n is odd, okay, so n is odd, that means that is 3, 5, 7, something like that. So, it is odd. So, then x star is an inflection point, that means whatever your x star is already a stationary point, but this stationary point will be an inflection point if n is odd. I hope this is clear. So, if n is odd, so n is n value if it is 3, then 5, then 7, something like that. So, in that case that x star is an inflection point. Now, if n is even, so n is even means the n equal to 2, then 4, then 6, something like that. Okay. So, in that case that is a local optimum. So, what is local optimum? The local optimum means either it may be a maximum point or it may be a minimum point. So, now then we will look at the derivative value. If the derivative is positive, that means this is a non-zero derivative and this derivative is positive. Okay. So, positive. So, positive means then x star will be a local minimum. Clear? So, now if the derivative is negative, okay, derivative is negative. So, in that case x star is a local maxima. So, let us remember that one. So, now what I will do, first I will look at the value of n. If n is odd, then x star is a inflection point. Now, if n is even, okay, so n is even, that means 2, 4, 6, something like that, then what I will do? I will look at the function value. Okay. So, if function value is positive, then x star is a minimum point. If function value is negative, then x star is a maximum point. So, by going through this, I can actually tell whether x star is a inflection point, it is a maximum point, or it is a minimum point. Now, let us see the proof, okay, how we can prove that one. So, proof is that suppose f of x star plus h. So, if I apply the Taylor series, okay. So, I can write f of x star plus h, which is equal to f of x star plus h f dash x star plus h square by factorial to second derivative x star and then plus. So, I can go up to this is h n minus 1 divided by factorial n minus 1 f to the power n minus 1 x star and this is h to the power n by factorial n f to the power n x star, that is the nth derivative. Okay. Now, since as per the definition the first derivative is 0 because that is stationary point, suppose second derivative is 0, third derivative is 0 up to n minus 1 derivative is 0. So, here the first derivative is 0. So, therefore, this will be 0, this will second derivative is 0 and n minus 1 derivative is also 0. So, therefore, I can write that f of x star plus h, f of x star plus h minus f of x star which is equal to h to the power n divided by factorial n, that n derivative at x star. Now, if n is even, okay, so if n is even, that means again I said that 2, 4, okay, 6 something like that, if it is even then what will happen, this value will be always positive because and if it is an even number, n is even number, then entire value will be positive. So, therefore, if the n derivative is positive, okay, so what does it mean? If this is positive, that means the right hand side is positive. So, in that case what will happen, f of x star plus h minus f of x star is positive. Okay. So, what does it mean? That if this is a minimum point and this is your x star, okay, and you are taking either h on this side or this side, that means f of x star plus h minus f of x star is positive. So, when it will be positive? If x star is a minimum. Okay. If x star is a minimum, so in that case this value will be positive. So, therefore, I can say if this value is positive then x star is a minimum, hence it is a minimum. Okay. Now, if the derivative, the n derivative is negative, okay, so in that case f of x star plus h minus f of x is negative. So, when it will be negative? In case of maxima. So, I can say that this is the case. So, this is your x star, this is your x star, and if you take any value either left hand side or right hand side. So, in that case what will happen, that f of x star plus h minus f of x star is negative in case of maximum. Okay. So, therefore, if it is negative then I can say that x star is a local maximum. Okay. So, what we are discussing here, if n is even, so in that case I will look at the derivative value. If derivative value is positive then f of x star plus h minus f of x star is positive, then I can say that this is a minimum point, and if derivative value is negative then f of x star plus h minus f of x star is negative, then I can say that is a maximum point. Now, if n is odd, okay, so in that case what will happen, this value will basically change its sign whether you are approaching from left hand side or you are approaching from the right hand side. So, this value will change its sign with the change in the sign of h. That means, if h is positive, that means you are approaching either from left hand side or from right hand side. So, what will happen, h will be either positive or negative. So, based on whether h is positive or negative, the sign of this value will change. So, therefore, in this case what will happen, if you are approaching from one direction this will be positive, and if you are approaching from the other direction then it will be negative. So, in that case that is a condition for inflection point. So, therefore, we can say if n is odd, so then the particular point is an inflection point. Okay. So, if n is odd, so in that case, because if you are approaching from one side then it will be positive, if you are approaching from the other side that will be negative. So, therefore, this is a condition for inflection point. So, in case of inflection point, as you have seen, the function value is increasing in one side and decreasing on the other side, or it may be other way also, that means increasing one side and decreasing on the other side. So, therefore, that is a condition for inflection point. So, I can say that if n is odd, so in that case x star is an inflection point. So, what we have discussed, let me summarize. So, what I will do, I will take the first higher order non-zero derivative value. Okay. So, suppose the order is n. Now, you look at n, if n is odd, then what you will do? If n is odd, then x star is an inflection point. Directly you said that is an inflection point, that is neither maxima nor minima. If x star is even, okay, so in that case you look at the function value. Okay. So, what is the derivative value? So, if x star is even, so you will look at the derivative value. Now, if the derivative value is positive, then x star is a minimum, and if the derivative value is negative, then x star will be maximum. Okay. So, that way I can tell a particular point, a stationary point, whether that is a maximum point, whether that is a minimum point, or whether that is an inflection point. Okay. So, I can tell looking at or going through these sufficient conditions. Now, let us see this example problem. So, I would like to solve this problem and find out the stationary point, and also I would like to find out whether the stationary points are a maximum point, minimum point, or an inflection point. So, what I will do, suppose for this particular function f of x equal to x cube minus 10 x minus 2 x square minus 10. For this function, what I will do, first I will apply the necessary condition. What is necessary condition? The first derivative is 0. So, let me take the first derivative. So, first derivative is 3 x square minus 10 minus 4 x equal to 0, and if I solve this particular equation, so I will get that x star is 2.61 and minus 1.28. So, that means I am getting 2 points, one point is somewhere here and that is minus 1.28, and I am also getting another point that is 2.61. Okay. So, looking at this particular curve, so I can say that this point is a maximum and this point is minimum, but let me apply the sufficient condition here. Okay. So, these 2 points are the stationary points. Why stationary? Because the first derivative is 0 at these 2 points. Okay. So, derivative is 0 here and derivative is 0 here. So, therefore, I can say that these 2 points are stationary points. Now, let me check whether these points are a maximum point or a minimum, okay, or an inflection point. So, to do that, what I have to do? I have to apply sufficient condition. So, what is sufficient condition? I will take the second derivative first. So, now second derivative I am getting 6 x minus 4. Okay. So, if I calculate the value of second derivative at 2.61, so I am getting 11.66. So, now in this case the n value is 2, that means even number, n is even number, this is second derivative, n is even number. So, n is even number, in that case what will happen? That will be either maximum or minimum point. Now, let us look at the derivative value. Now, derivative value is 11.66 and which is positive, and therefore, that x star equal to 2.61 is a minimum, okay, minimum point, that is 2.61. Here the second derivative value is positive. Okay. So, therefore, is positive. So, and n is even because the second derivative. So, therefore, x star equal to 2.6 is a minimum point. Now, let us look at the other point, that is x star equal to minus 1.28. So, here the derivative value is minus 11.68, that means negative, and n is even and the derivative value is negative. So, therefore, this is a maximum point. Okay. So, that way by applying necessary condition and sufficient condition, so I can find out the stationary points, all the stationary points, and also I can tell that a particular stationary point is a minimum or maximum point or an inflection point. So, what I have to do? I have to apply the sufficient condition. So far we have discussed the necessary and sufficient conditions for optimality in case of single variable optimization problem. So, we have only discussed the single variable optimization problem, but what is the necessary and sufficient conditions for optimality in case of multivariable optimization problem. So, let us discuss that one. Let us define a multivariable function, that means I would like to find the minimum of this particular function f x. So, where x equal to x 1, x 2, x 3. So, it has n variables. So, necessary condition for optimality is if f x has an extreme points, that is maximum or minimum at x equal to x star, and in this case x is a vector, okay. And if the first partial derivative of f x is exist at x star, then the partial derivative of f with respect to x 1, x 2, x n should be equal to 0. That means, partial derivative with respect to the variable, suppose we have two variables, then in that case del f by del x 1, del f by del x 2 should be equal to 0. So, we have n variable. So, in that case del f by del x 1, del f by del x 2, then del f by del x n up to del f by del x n should be equal to 0. So, that is the necessary condition. By applying that, so I can find out the stationary points, that means whatever x star I am getting. So, that x star may be a maximum point or minimum point or an inflection point. So, we have to apply the sufficient condition for optimality. The sufficient condition for stationary point x star to be an extreme point. Extreme point means either it is a maximum point or minimum point or an inflection point. To be an extreme point is that the matrix of second partial derivative of f x evaluated at x star is positive definite. Okay. So, when x star is relative minima. So, whatever the matrix I am getting. So, the matrix of second partial derivative of f x evaluated at x, if it is positive definite, then x star is a relative maxima. If it is negative definite, then x star is a relative maxima. Neither positive nor negative definite matrix, then x star is neither minima nor maxima, then in that case that is a saddle point. Okay. So, in this case what we have to do? We have to take the second derivative, second partial derivative of f x. So, I will get a matrix. Now, what I will do? I will evaluate that matrix at x equal to x star. If the matrix is positive definite, then x star is a minimum point. If the matrix is negative definite, the point is a maximum point. If the matrix is neither positive nor negative, so in that case that x star is neither maxima nor minima, it is a saddle point. Now, let us prove that one. So, we can apply the Taylor series. So, in this case I have considered two variable function. So, I can write f of x plus delta x, y plus delta y. So, I can write it f of x y plus delta x del f by del x plus delta y del f by delta y, then 1 by factorial 2 within bracket del x square, then del square f by del x square plus twice delta x delta y del square f by del x del y plus delta y square del square f by delta y square. So, I am not considering the higher order derivative. Okay. So, if I write in matrix form, so I can write it something like that. So, f of x y, then del x del y, then del f by del x and del f by del y. So, I can write, and I am getting this particular matrix, and this matrix is known as Hessian matrix. Okay. So, now I can write it something like that in matrix form, that this is f of x star, then H transpose, then del f at x star, and 1 by factorial to H T H H. Okay. So, in that case, if I write it something like that, that x star is a stationary point, x star is a stationary point. So, therefore, this term will be equal to 0. Okay. So, in that case, what I can write, that f of x star plus h minus f of x star, which is equal to 1 by factorial to H T H H. Okay. Now, depending upon what is this value, whether this value is positive or negative. So, if it is positive, then what will happen? If it is positive, then f of x star plus h minus f of x star is positive. In that case, x star will be minimum. And if this is negative, okay, so if this is negative, so in that case x star will be maximum. So, now question is that whether this right hand side is positive or negative. Okay. So, now x star will be minimum if this term H transpose H H is positive, and x will be maximum if H transpose H H will be negative. Okay. So, now this term H transpose H H will be positive if H is a positive definite matrix. Okay. So, I can check actually whether H is a positive definite matrix or negative definite matrix, and if this term will be negative if H is a negative definite matrix. So, what you have to do basically, you have to look at this particular Hessian matrix. If the Hessian matrix is positive definite, so in that case that will be a minimum point, and if Hessian matrix is negative definite matrix, so in that case that is a maximum point. If the Hessian matrix is neither positive nor negative, in that case the x star will be neither maximum nor minimum point. So, a matrix H will be positive definite matrix, that means how we can check whether the Hessian matrix will be a positive definite matrix or not. So, a matrix H will be positive definite if all the eigenvalues are positive. So, what I can do? I can calculate all the eigenvalues of this particular matrix. If all the eigenvalues are positive, so in that case I can say that H is a positive definite matrix. Okay. That is, all lambda values are positive which satisfies the following equation. Okay. So, all the lambda values will be positive which satisfy the following equation. So, what I can do? I can calculate the eigenvalues. If eigenvalues are positive, so in that case I can say this particular Hessian matrix is a positive definite matrix. Or otherwise, there is another test, we can evaluate the determinant. Okay. So, what I can do? Suppose this is my Hessian matrix. So, A1 is the first value, that means this one, A2 is the second order, then the third order, something like that. So, if I calculate A1, A2, A3 up to An, now a matrix A will be positive definite if and only if all the values, that is A1, A2, A3 up to An are positive. So, if A1, A2, A3 and An are positive, so in that case I can say that A is a positive definite matrix. The matrix will be negative definite if and only if the sign of A j is minus 1 to the power j for j equal to 1 to 3 up to n. Okay. So, if the value of A1, A2 or A3, okay, so the sign of the A1, A2, A3 follows this rule, that is minus 1 to the power j, j means suppose j is equal to 1 to 3, that means A1 should be negative, A2 should be positive, A3 is negative, A4 is positive, something like that. So, in that case I can say that is a negative definite matrix. So, I can apply any one of these two. So, either I can check the eigenvalues, if eigenvalues are positive, So, in that case I can say it is a positive definite matrix, or I can also calculate A1, A2, A3 up to AN and look at the sign of A1, A2, A3, AN. So, if it is positive I can say it is positive definite matrix, if it is follow minus 1 to the power j. So, in that case I can say it is a negative definite matrix. So, let us see an example problem. So, I would like to solve a simple example problem that f of x1 and x2, so two variable problem, and that is x1 minus 10 whole square plus x2 minus 10 whole square. So, solution of this particular problem is known to me, the solution is 10 and 10. So, I have plotted it. So, this is the solution and this is the x star value. So, x star value is 10 10. I have also shown the surface plot of this particular function. So, let us apply the necessary condition. So, what necessary condition will give? Necessary condition will give me the stationary points. Okay. So, necessary conditions are del f by del x1, that means the partial derivative with respect to x1 and with respect to x2 should be equal to 0. So, if I take the derivative of this particular function, then with respect to x I will get twice x1 minus 10 equal to 0, and if I solve it then I will be getting x1 equal to 10, and similarly if I take the derivative with respect to x2. So, in that case I am getting x2 equal to 10. So, therefore, x star is the stationary point, that is 10 and 10. Okay. So, this is the solution of this particular problem, that is 10 and 10. Now, question is that I know in this case this is a minimum point, but let us see by applying the sufficient condition for optimality. So, in this case the Hessian matrix should be a positive definite matrix. Okay. So, let us apply the sufficient condition. The Hessian matrix is del square f by del x square, del square f by del x del y. So, in this case x1 and x2. So, I have written del x del y, and similarly this is del square f by del x del y and del square f by del y square. So, if I do that, if I take the derivative of this one, so finally I am getting 2 0 0 2. So, this is the Hessian matrix. Now, I have to check whether this Hessian matrix is positive definite or negative definite. So, what I have to do basically, so I have to check whether this Hessian matrix, that is 2 0 0 2, is a positive definite matrix or a negative definite matrix, or neither positive nor negative. So, in this case I know this is a minimum point. So, therefore, the matrix should be a positive definite matrix. Okay. So, let us see, I can calculate the eigenvalues. So, if I calculate the eigenvalues, so eigenvalues of this Hessian matrix 2 and 2, that means both are positive. So, therefore, the Hessian matrix is a positive definite matrix and x star is a relative minimum. Okay. So, I have calculated here the eigenvalues. So, eigenvalues are 2, positive 2 and positive 2. So, therefore, this matrix is a positive definite matrix and therefore, x star is a relative minimum. Similarly, I can also calculate what is A1. So, A1 equal to 2 and in this case A2 equal to 4, and both are positive. So, if both are positive, A1 A2 are positive. So, in that case the matrix is a positive definite matrix, and therefore, the Hessian matrix is a positive definite matrix. So, therefore, I can say that x star is a relative minima. So, I have also shown you the contour map here. So, you can see from the contour map also this is a minimum point. So, just I have shown you using the Hessian matrix also. The Hessian matrix is also a positive definite matrix and therefore, x star is a relative minima. Okay. So, that is all for today. So, we have discussed the necessary condition for optimality in case of single variable optimization function, and we have also discussed the necessary and sufficient conditions for optimality in case of multivariable problem. Thank you.